So after an exam, I was explaining to my students how they got a certain problem wrong. It involved maxes and mins. And as I was explaining to them why they got it wrong, I was kind of going through the why of how the second derivative tests work. And as I was explaining to them, they were a little frustrated. They're like, "Hey, why didn't you, I wish you would have told us to explain like the why behind it earlier, because if you did, that would have helped us understand it. It would help us remember it. And if we see something like this, we'd be able to have some kind of intuition to fall back on if we forgot the exact rules of the second derivative test." So that's what this video is about. It's about understanding the why and the how behind the second derivative test and the discriminant. So you're probably familiar with the discriminant. It's defined as the second derivative of your function f with respect to x at a and b times the second derivative of your function x with respect to y at a and b minus the partial derivative of x and y at a and b squared. And you're probably familiar with what the rules are. And just for a review, the first one says if d is greater than 0 and your second derivative with respect to x is greater than 0, then you have a local minimum. If d is greater than 0 and your second derivative with respect to x is less than 0, then you have a local maximum. If d is less than 0, then you have a saddle point, and if d equals 0, then the second derivative test is inconclusive. But why does this work? Well, the part about f sub xx and it being greater than or equal to 0 is probably the easiest part of this to understand, and it just simply goes back to what you're familiar with from Calc 1, from differential calculus. If you recall back in differential calculus, when you find that critical point, you could tell if it was a max or a min by taking its second derivative at that point. For example, if the second derivative was positive at your critical point, as it is here, that means the curve is going to be concave up at that point, and if that curve is concave up, you know that that point is going to be a local minimum. And that is basically what the first line of the second derivative test is telling you here. If the second derivative with respect to x is greater than 0, then that critical point is going to be a local min. The second line basically states the opposite. If that second derivative with respect to x is less than 0, then it's concave down at this point, and you're at a local maximum. So this hopefully provides just a little bit of intuition for that, for lines 1 and 2. But let's just consider an example. So imagine the surface f of xy equals x squared plus y squared. Or easier than imagining it, how about I just pull it up in Calculate 3D. So this will have a discriminant if I take those second derivatives of d is equal to 4, which is greater than 0. And it's going to be concave up in the x direction at this critical point 0, 0, so we know it's going to be a local min. Now, throwing in some negative signs here, we'll just change this equation around and say that our f of x is negative x squared minus y squared. Well, it turns out we still have a discriminant of d equals 4, which is still greater than 0. It's because those two second derivatives are both negative. If you multiply two negatives, you still get the positive. So we got the same d. In this case, it's just going to be concave down. So that second derivative test gives us a local max at the point 0, 0 in this case. But what if we changed it to f of xy equals x squared minus y squared? So it's still going to be concave up. If we just look at this graphically, it's going to be concave up in the x direction, but in the y direction, as shown by this blue trace here, it's going to be concave down. So we don't have a local minimum at 0, 0 anymore, or max, we have a saddle point. And just to see how the discriminant works for this, in this case, our discriminant is going to be as defined above. And if we take the second derivative with respect to x, we get 2. If we take the second derivative with respect to y, we get negative 2. And that mixed partial derivative is going to be 0. So we end up with negative 4 for our discriminant, which now is less than 0. So why did we get a discriminant that's less than 0 in this case for the saddle point? Well, it's because that term, that first term, the second derivative with respect to x and the second derivative with respect to y, you multiply those together and it's negative. Well, why is that term negative? Well, it's negative because those second derivatives with respect to x and the one with respect to y have different signs. And this is the most basic way that this discriminant gives you a negative number showing a saddle point when you're concave down in the x directions, for example, concave up in the y direction, or vice versa. It's pretty obvious that's going to be a saddle point. And in this case, it doesn't even matter what that mixed partial derivative is going to be, because if that term, if that first term is negative, and then you're going to go ahead and subtract this f sub xy at a and b squared, well, you know that term you're subtracting is always going to be positive because it's squared. So you're taking a negative number and you're just subtracting from that. You're still going to end up with a negative number. So regardless, if you've got concave up in the x and say concave down in the y, you're always going to get a d is less than 0, and you'll show that's going to be a saddle point. But what is the point even of that mixed partial derivative term? Why do we even have to consider that? Well, the basic answer is things get more complicated in 2D because now we've got cross terms. So let me give you an example here. Consider this surface similar to that first one, just x squared plus y squared, but now we're going to have a cross term, and we're just going to add a times x times y. So if a is equal to 0, well, this is simple. We've already looked at this. It's our earlier parabola that's concave up in the x and y directions, and that critical point 0, 0 is still a minimum. But what happens when we start increasing a here, this cross term? So you can see as we increase a, that critical point is changing from being a minimum to becoming a saddle point. So since we have a saddle point, that means that it's going to be concave up in, say, the x direction and concave down in the y direction, or vice versa, right? Because it's a saddle point? Not really, and not actually at all. If we say we trace this x curve out on our surface here, we'll see that it's in the red here, and it's still going to be concave up in the x direction. And if we trace out the blue line over our surface in that y direction, you see it's still concave up in the y direction. So it's concave up in the x and concave up in the y, yet it's still a saddle point. And why is that? Well, just graphically looking at this, you can see that it's concave down in that sort of that mixed direction, that diagonal direction that includes both the x and the y. So that's what this cross term does, is it sort of accounts for that diagonal between them. So let's just think about this based on the calculations here. So when a equals 0, we get d is greater than 0, and so we know that's a local min, as we looked at initially. But how about when a equals 2? The two different terms will actually cancel out, and as you can see here, we're not going to have a max or a min or even a saddle point at that point 0, 0 anymore. And then if we crank up a up to 4, say, now that basically that cross term has dominated that first term, so d is going to be less than 0, and now we have a saddle point. So that cross term is probably the least intuitive piece, and it comes because we got two dimensions. We got cross terms now. But hopefully this gives you sort of a feel for how the discriminant and the second partial derivative test can work to help you identify maxes, mins, and saddle points. So until next time, take care.